would like to state what I think is a fairly interesting additional open problem about these advice time trade-offs for inverting one-way functions and one-way permutations, which is to understand what happens when the inverter is a quantum algorithm, possibly with advice. Okay. So let's recap. What we said was that both are interesting. Both classical advice and quantum advice are interesting. So to recap, let's say that we have S bits of advice. So we have that in the, say, classical setting, the time to invert is at most n divided by s, or epsilon n divided by s if you're looking at inverting on an epsilon fraction of inputs, up to some polylog factors, and by lower bounds you can prove either by pre-sampling or compression. This is tight. So what can you do in the quantum setting? Let's say with classical advice. So first of all, you could just do Hellman's algorithm. So you get the same upper bound. But also, you can use Grover's algorithm. So Grover's algorithm solves any kind of brute force search problem in square root of the search space. Let's say you want to invert on an epsilon fraction of inputs. You can just sort of try to invert the lexicographically first epsilon n inputs. And so then you get order of square root of epsilon n. Right, so this is an algorithm that uses zero advice. This is an algorithm that uses zero quantumness. Yep. So you would kind of expect to have now some kind of way of combining them. But this seems very difficult because the idea in Hellman's algorithm, and really in any algorithm that improves over brute force search, is to compute f of f of f of f and so on. And this kind of pointer chasing problem is actually provably hard for quantum algorithms. So, so we really don't know any upper bound that is better than the minimum of those two quantities.
Sorry, what is hard? The chaining computation?
Yes.
It has been proved?
I mean, so it has to be defined precisely. So we are in an oracle setting. There is some oracle permutation. I give you x and k, and I want you to compute f of f of f of x k times. That requires something like omega of k queries. Okay. Right. So the best upper bound that we know is just the minimum of those two quantities, and I think it would be a really nice result to argue that this is tight. That really either you have advice more than root n, and then you don't need to use any quantumness, or your advice is less than root n, and then there is no use for the advice. So we have proved with Aronson, Bulatov, and Narievi a weaker lower bound, which says that up to some polylog factors, you need time at least square root of epsilon n over s. Okay. So this matches Grover's algorithm if you are not given any advice or very little advice. But it's, in my opinion, very unlikely case that this lower bound is tight. It would mean that you can always improve Grover's algorithm by some use of advice. Okay, so this is the gap between upper bound and lower bound. So maybe I'll tell you a little bit about how this lower bound is proved. Sorry, good question. So, so this lower bound is proved for classical advice. There are many results, but not kind of case-by-case results, that says that, so what you can do with quantum advice is not better than what you can do with classical advice, especially when it comes to compressing things and so on. So I would expect that it's possible to prove the same lower bound also for quantum advice, although that's also an open problem. And I would still think that it's not possible to improve over those algorithms even if you're given quantum advice, because again, it's not clear how that would help pointer chasing, which is intuitively kind of all you can do when you are given oracle access to a permutation.
What about quantum advice and classical queries? You don't expect, can you prove,
What does it even mean, quantum advice?
Ah.
Oh, that's an interesting question. I would think that we can prove. I would think that we could prove this with quantum advice and classical queries, but
Because there are counterexamples in like bounded storage models. There
yeah.
are artificial guys.
No, actually, yeah, I wouldn't state a yeah, I don't know, but we didn't even think about that. Maybe that's a good question. Yeah.
What about non-adaptive query algorithm?
We also.
Easier to be rolled out?
Our argument would not improve, but you would expect that the non-adaptive case is easier, but our lower bound will not improve.
But isn't Grover inherently adaptive because it does everything?
Grover is Grover adaptive? Oh yeah, because you do the flipping. Yeah, but the question was for the lower bound. I don't know if you can prove a stronger lower bound assuming that things are non-adaptive.
So is a dream version of pre-sampling that would give tight things? Because I guess you're going to do compression, right?
Yes, I don't know what. I don't know how to state something about pre-sampling that would. I mean, maybe someone. I should ask you this question. Why are you asking that to me? That's, okay. Yeah. So let me tell you a bit about what the lower bound looks like. The square root of epsilon over s, assuming that you have s classical bits of advice, and you have this quantum adaptive algorithm. So the idea will be again to imagine some kind of compression procedure where the compressor and the compressor share some randomness, and the compressor will send the value of the function restricted to a subset of the input. And so as long as actually in this case, even if this communication was quantum, the things would work, but there are some subtleties. But anyway, so this would be a classical communication of just some subset of the function. So really the quantumness of the algorithm just goes into deciding sort of what subset of the input you can get rid of and still allow the decompressor to use the inverter in order to figure out what were those missing entries. So one of the first difficulties that comes in trying to do this is that in the classical case, we could either assume that the inverter was deterministic, or if not, say that the common randomness between compressor and decompressor stores the randomness of the inverter, and then essentially, without loss of generality, you have a deterministic inverter. But in the quantum case, you cannot sort of de-randomize the quantumness. This is sort of inherent. So perhaps what I will show this will give, I think, a good idea of then what goes on in the proof, is to argue how you could actually repeat the argument that I did earlier in the classical case, but without sharing the randomness of the inverter between compressor and decompressor. Because then that's very similar really to then what will happen for the quantum case. Yeah?
But whatever you're proving, your proof also has to include the lower bound of Grover search, right?
For sure, yes.
So, but that's not, this is not how it's usually proven using compression algorithms.
No, but sort of something that we will use to argue that the decompression works includes an inequality that implies the tightness of Grover. So this will go into the correctness of the reduction more than the definition of the reduction. Okay. So the definition of the reduction will be very similar in the quantum case to what would happen in the classical case, provided that you're not allowed to share the randomness of the inverter between compressor and decompressor.
So you're still showing compression. You're still showing like in the end how to compress the entire organ. It's not like you're not going via like these random access codes or things like that sort of break the problem into a problem of like sort of just recovering one value or the.
Yeah, because if I could do the argument using random access codes, then this would also work, I would assume, for quantum advice. Yeah.
Like you can or you don't want to?
I don't know how. Yeah. Right. So let me show you what you would do in the classical case if you're not allowed to share the randomness of the inverter. So you will again pick a random subset of size 2 to the n over t of the possible outputs. And actually, I didn't mention it, but this idea of looking at this random subset to improve the compression was a paper of Wee, not the work of Rosario Gennaro and I. So let's say we have, so let's say that to get started, we first pick a certain random subset of the possible outputs of the bijection, and we cannot commit to the fact that in our compression, what we will omit will be a subset of these blue input-output pairs. Okay, so what subset of the input-output pairs? So the compressor will do the following reasoning. For each of these blue pairs, it will look at what is A doing on input Y. So then the inverting algorithm will make queries, and those queries are random variables that depend on the randomness of the inverter. So it will say that Y is good if the probability over the randomness of A that A queries a blue input is, let's say, less than a quarter. All right, now A makes T oracle queries. Let's say that this blue set was chosen to be of size 2 to the n divided by 10 times t. Yeah. So and kind of the randomness of the algorithm and the randomness of the choice of this random set are independent. So the typical run of the algorithm has only a probability at most 1/10 of making a query into a blue element. So then you can do kind of Chernoff bounds in terms of the randomness of R. For most of the, actually even for most of the blue elements, the probability of being good is pretty high.
It could be that A is like stupid and always queries the same element for all. Like this probability could be A could always query the same element to begin with, and then independently of Y. And then if you were unlucky and chose it as part of blue, then there's no good Y at all. And this is a probability over the blue stuff, not over.
Right. But then it's it will not be 1/4. It will be it will be like 1/t.
If you take probability over the blue choices.
Yeah.
Okay, I thought you fixed already the blue choices, and now you're looking at the probability of.
Right. But kind of both things are random. I want to say, for a fixed choice of the blue vertices, this is which vertices are good. Now, randomize everything, then most vertices are going to be good for most choices of R. So there is a choice of R for which most vertices are good. Okay. So then I will, here, what I will omit will be the input-output pairs that are blue and good. Okay? So there are almost all of these 2 to the n over t input-output pairs. So then how is the decompression working? I'm looking at one of the elements that are missing from the encoding. So the decompressor needs to figure out what it was. So it will run the inverter on that element y. And now there is some chance that it will actually query some of the blue elements, maybe even some of the good blue elements which are missing. And then those runs of the inverter will fail. But at least 3/4 of over the randomness of the inverter, with probability at least 3/4, A will invert Y without querying any of the blue elements. In particular, without querying any of the missing elements. Okay. So since here everything is computationally unbounded, it can just enumerate all possible random choices of A and figure out what was the inverse. Okay. How much time is left? Okay. Yeah, it's plenty. Let's not. Let's get to lunch quickly. All right. So how do you go from here to quantum? Yeah. So I want to have a kind of similar notion. So I want to kind of again pick blue elements with some density, except that this density will be higher. So it will be more like this much over t squared. Although why it's that will come up later. And then I want to still think about some notion of a y being good if the inverter applied to y doesn't query blue inputs with high probability. Okay. So for this, so I guess in this case, the analogy would be what is the expectation over the randomness of A of the number of blue queries made by A. So this would be the classical analog. Now I would like to look at a kind of analog of this in the quantum setting. Yeah. So what I will look at is the sum will be the so sum of the amplitudes of all the computational paths that the inverter can do, which involve making a blue query. Okay. So I guess here one would have to define this quantum model a bit more, I mean, with a little bit rigorously. But I guess for the sake of just getting a sense of what the algorithm looks like, we can think, as in the random case, that the inverter has multiple things that it can do. And for each of the things that it can do, it will make certain Oracle queries, do some computation, and produce a certain output. Now, in a probabilistic case, each of those possible computations has some positive or non-negative probability, and those probabilities add up to 1. In a quantum case, each of these possible computations has some amplitude, which could be an arbitrary complex number, although without loss of generality will be a real number. And now it's possible that you have kind of positive and negative things that cancel out. But you can still look at, say, what is the sum of the, say, absolute values of the amplitudes which involve making a blue query. Okay. So we're going to look at something like the sum over Q being blue, or some kind of sum over computation, maybe Y or X, computation that queries X of okay, and the important thing is that for if you sum over all is that for every X, this is at most T. Is that what it is?
So computation involves multiple queries. So amplitude of computation is you add them before taking the absolute value. So query X might be partially kind of touched in every query of the computation.
Yeah, then I'll count it multiple times. But if I make at most T queries, yeah, I think what's happening here is that the sum over all X's, not even just the blue ones, will be at most T. Okay. So if I look just at the X's that are blue, then with high probability over the choice of the blue set, this will be at most T times 2 to the n divided by r. T times r divided by 2 to the n. So this will go down by the density of this random set that I'm choosing. Or maybe an extra constant to allow some concentration bound. Okay. All right. Now, if my set is of size 2 to the n divided by order of T squared, I can make this smaller than order of 1 over T. Okay. All right, so now something that sort of implies Grover has to be done. And so this is the kind of quantum argument lower bound part. So I will define a blue X to be good if if this quantity for that X is less than sorry, this is. What is this somewhere? Yeah. So we'll define a blocks to be good if the sum of amplitudes of being queried is sufficiently small. And then the compression will be the same. I will send over f restricted to the value of f on all the input-output pairs except the good blue ones. And now I want to argue that the decompressor can figure out those missing entries. Yeah.
About emulating quantum algorithm using partial information when it's basically emulated.
Yeah, exactly.
But inefficient, you don't need to do efficient. You can emulate it like.
Yeah. The decompressor has unlimited running time. The only question is, is f restricted to all the entries except the good blue ones enough to emulate the inverter on all inputs? Yeah, exactly.
Replace it by 0 and pretend to do the whole thing.
Exactly. That's exactly right. So what the decompressor will do is to kind of create a new function f hat, where f hat it's like f on the input that it knows, and whatever some kind of fixed, just some arbitrary permutation on the others. So then for each y, well, there are some y's already knows. So really, for every missing y, it will run the inverter A on this. And then what is the statistical distance of the inputs of A on the true F versus A on this F hat? So this is where this inequality that implies Grover comes in. This difference is at most order of square root of t times the sum of the amplitudes of the queries in which those two functions differ. So if we manage to get that to be less than 1 over t, this will be a small constant. And then just kind of enumerating all possible things that the algorithm can do, we can find the inverse. So then tracing it all back, it means that the kind of points that we can omit are a constant fraction of this set of density 2 to the n over t squared, which means that the kind of space that we have saved, the space that kind of defines what advice must have been contained into the inverting algorithm, must be at least 2 to the n over t squared. So if the space is at least 2 to the n over t squared, means the time is at most the square root of 2 to the n over s. Yeah. So this is, seems for this argument, it's difficult to improve, probably something a little different from a compression argument should be done to get any improved lower bound. In particular, any improved lower bound should be able to say that pointer jumping is hard for quantum algorithms. Because if pointer jumping was easy for quantum algorithms, if you had the quadratic speed up, then this bound would be tight because you would just do like Grover for Hellman. And none of the techniques that I've talked about have any implication for the complexity of quantum pointer jumping. So that's why it seems that a substantially different setup is needed to prove any tether bounds. Okay, I think I can stop here. Thanks. So in the case of quantum advice, then what would happen is that so this inverter gets oracle access to F, but also takes as input, as is common for quantum, it takes input a quantum state. And that quantum state is the advice. And the length of that is just how many qubits that quantum state is.